Già si può avviare già la registrazione. Passato di un po'. Ich versuche es laut genug zu machen, dann hat sich jemand beschweren, das wohl.
My name is Marita Sander. I'm from the University of Rostock. I will chair this session in the afternoon. And the first speaker is Sebastian Münstermann from the Technical University of Aachen. And it's your turn.
It's my turn. Okay. Also switched on. Thank you very much. Okay. Can you hear me like this?
Yes.
I will not use the microphone. In fact, I'm going to give two presentations. The first one will deal with the high cycle fatigue behavior and microstructural influence on the fatigue strength of structural steel. And the second presentation I'm going to give afterwards will deal with the ultra-low cycle fatigue. So in fact, there are some very different mechanisms behind this. With the presentation I'm going to start, I would like to highlight how one can quantify the microstructure influences on the endurance fatigue strength of structural steel. There are some very famous rules that that serve to express microstructural influences on the endurance fatigue strength of steel. The most famous one, to my understanding, was given by Murakami. And he mentions that, use the pointer, he mentioned that the major microstructural influence on the endurance fatigue strength of steel is given the maximum inclusion size. So it doesn't, it's not of a very significant influence how many inclusions you have, but the major contribution comes from the size of the biggest inclusion you have got in your microstructure. In other words, according to these findings, it does not play an important role if the microstructure looks like this or if the microstructure looks like this. But both these images come or were made for steels of the same grades. Both of them are steels of the strength of a guaranteed yield strength of 355 megapascal. The question I would like to answer with my presentation is if we can express the fatigue limit of steel as a function of microstructural parameters like grain size, grain shape, grain orientation, degree of bending, and so on. Okay, to understand how we can express this, we also need to understand the mechanisms of or the fatigue mechanisms of steel, especially in the early fatigue stages. So you can here see an illustration which shall be the total lifetime of a component under cyclic loads. And you see that we've got a crack incubation phase. This is a phase on a very, very small length scales. The first cracks are formed. Usually that happens, or that can happen at inclusions. Then we will have a very long period where mainly short cracks are growing due to the cyclic loads. And then, and of course, the shell somehow depends also on the applied stress level. There is a somehow shorter period where we've got the long crack growth, and finally a very short term, which is the final fracture. In fact, this is, let's say, almost zero of the lifetime, but then you wouldn't be able to read the word fracture. So I reserved some significant space for this. So what we understand is that short cracks make up the major portion of the component's lifetime. And the fatigue damage mechanism in this phase for the short cracks is the creation of persistent slit bands, which govern mainly the incubation phase and also the short crack phase, and then the subsequent fatigue crack growth. And for short cracks and long cracks, there's a certain transition in cyclic growth mechanism. What's very important, especially for steels, is that interfaces are barriers for short cracks, at least if the applied stress amplitude is not sufficiently high. So it means that a short crack can grow, but it will, if the stress amplitude is not sufficiently high, for a longer period of time and for a significant number of cycles, it will not be able to pass this barrier and then run into the neighbor grains. And for the endurance fatigue strength, we observe that the incubation phase and the short crack growth phase are completely run through, but there is no transition to long crack growth. Okay, in other words, if you load a sample in the region of the endurance fatigue strength, you will see a lot of cracks inside, but they are very, very short. They are not long cracks, they are short cracks that simply stop at these boundaries unless you provide a very, very high cycle number, or in case that you increase the applied stress amplitude. I would like to mention about the general approach that we have used in here. So we have performed a systematic parametric study on artificial microstructure models in order to identify these microstructural influences on the endurance fatigue strength. We have investigated 81 different microstructural configurations, which were tested on 9 different stress amplitudes. For every configuration, 20 statistically representative volume elements or microstructure models, is the better words, were used. The topics I would like to address today is, first of all, how can we create the statistically representative microstructure models, how to quantify the fatigue relevant loads, and how to numerically predict the endurance fatigue strength. So let's speak about the algorithm to create statistically representative microstructure models. Here you see an EBSD image of the steel, of a typical steel of the grade S355. You see that the microstructure, or you can expect that the microstructure is made up by ferrite and by pearlite. And the colors here indicate the crystallographic orientations of the ferritic phase. And then you can first of all measure the phase fractions for ferrite and pearlite, and then individually you can also measure the grain size distribution of the ferritic phase and of the pearlitic phase, and you can also find suitable distribution functions to express these findings. Of course, what's also important are some morphological parameters of the microstructure, for example, the elongation of grains, the morphological orientation with respect to the rolling direction. Also, this can be measured by the same approach, and then you can run the so-called random sequential addition algorithm. This is an algorithm that puts the seeds for the later grains into the predefined box. And of course there are some laws that you have to reserve a certain space where no other seeds may be placed. Once you have put your seeds into the box, they should not be moved anymore, and of course there may be no intersections of these boundaries that we've reserved for the grains. And then you run the multiplicatively weighted Voronoi tessellation algorithm and you create such a microstructure model. Just to mention, we are also able to consider these elongations of these banded kinds of microstructures, which are quite often present in pearlitic steels. And for fatigue investigations, this is really important. We also need to consider the inclusions. And the inclusions are addressed on the one hand by their average diameter and on the other hand by their shape. As a shape factor, and of course the diameter is given. The shape factor can vary between 0 and 1. If it is 1, then the inclusion has got a circular shape, whereas a significantly smaller number than 1 means that there's a very polygonal shape of this inclusion. Also here, we have, you will later also see this, write both the inclusion diameter and the inclusion shape. Okay, now we've got our microstructure models and we need to describe the constitutive behavior of the individual phases. We've observed in some experimental investigations that the paralytic phase was not that important because we saw that the incubation happens in the ferritic phase. Therefore, we cared for this quite a lot and we have used a crystal plasticity model to express the hardening behavior of the ferritic phase. And here you see it's a phenomenological model that does not consider strain gradients, but at least it considers the kinematic hardening. So it's a combined kinematic isotropic hardening model that we have used. For the isotropic part, we have performed nano-indentation tests in order to fit these phenomenological parameters. The target functions for the load indentation depth curve, and also the pileups that we have that were created during the indentation. And likewise, you could also find the set of parameters. It's to be noted that we also tried to consider some Hall-Petch relationship in this model. So in fact, we invented grains of significantly different diameter in order to find a Hall-Petch relation for this crystal plasticity model. Here you can then see some experimental results that were done, that were achieved in stress-strain experiments. You see how we calibrated the kinematic hardening parameters, and here you see in red the contribution of both kinematic and isotropic hardening. You see good agreement to the experimental results, so we believe that this is expressing the reality quite well. And then we had to think about how to quantify the relevant loads. Of course, this is done with fatigue indicator parameters, and as this early stage of fatigue damage is very much related to the slip irreversibility, we believe that the accumulation of dislocation slip is a suitable fatigue indicator parameter for this early phase of fatigue damage. Of course, there are also other fatigue indicator parameters, a very famous one by Fatiguist and Sosi. And in fact, we tried to combine them and resolve them on the individual slip systems. So here you see that both the normal stresses on the slip system and also the accumulation of plastic slip were considered in this. We also performed some experimental investigations to see these short cracks. You see an experiment in a 4-point bending configuration with a notch on the unusual side of the sample. And here you see such a short crack which has started to grow starting from the inclusion and then also stopped for a certain period of time at this paralytic constitutive of the microstructure. And here you see our simulations stopped at different or evaluated at different cycle numbers, and you can really see that our fatigue indicator parameter also kind of predicts the crack growth direction quite well. Okay, so we can express the fatigue indicator parameter in the zone very close to the inclusion. There is also a certain crack propagation law available for these short cracks, a kind of DADN rule, similar to the Paris law. And of course, with increasing length of this short crack, becomes more probable that the crack will have a transition to a long crack. So also here we have to use a statistical description. We believe that the crack at the end of the incubation phase will have a length which is more or less the diameter of the ferritic phase. There's a certain number of cycles in the incubation phase which mainly depends on the fatigue indicator parameter in the vicinity of the inclusions. And we also believe that once the crack has reached, the short crack has reached 3 times the ferritic grain diameter, it should become a long crack, at least with a probability of 50%. So here we could also calibrate this relative distribution function law. And then we could apply different stress levels and express the influence of stress amplitude on the number of cycles at the end of the short crack period. And also we know that roughly at 5 million cycles there will be this the barriers that become active. So here we cannot trust our simulation result anymore, and we should really run into the endurance fatigue strength. We have tested, that's difficult, we have tested almost 14,580 configurations for our microstructure models, because we varied 3 ferrite grain sizes, 3 perlite colony sizes, together with also 9 configurations of the inclusions of the particles. We made, as I mentioned, 20 RVEs per configurations on 9 stress levels. In fact, we then used design experiments to reduce the number of simulations to be performed. And here's what turns out. You can see, and this is not a surprise, that the inclusion size plays a very important role. Also the inclusion shape plays a very important role, but you can also see that there are some minor contributions coming from other microstructure parameters. The most important ones are listed in here, so it's mainly also the relationship between the ferritic and the perlitic grain size. To sum up, I've presented a method to quantify the microstructural effects on the fatigue limits. This one is based on simulations with artificial microstructure models. They were done in 2D with plane strain assumption. I've been speaking about the CPFEM approach that we used. I've also mentioned that 2 fatigue indicator parameters were used, and I could reveal some more or less important microstructural influence on the fatigue strength of this material. With this, I would like to thank you.